So first, a little history lesson. There are other distributions besides a normal distribution, right? There's actually a lot of other distributions, but the one we're going to be interested in is something called the student's t distribution, right? You see, what happened was in the early 20th century, a statistician named William Seeley Gossett was working in Dublin for the Guinness Brewing Company. And his job was doing quality control, but he ran into trouble having to work with small test batches. The small sample size made it hard to get accurate results using a normal distribution. So when Gossett published the distribution that he worked on to solve this problem, he ran into another problem. His employer wouldn't let its employees publish their work under their own name, because the brewing world in Ireland was a small one, and if their competitors saw an article published under the name of one of their employees, it would give hints, right, about the processes they were developing. So just to get around this, Gossett published his results under the pseudonym Student, and the name stuck. Today, the distribution is still referred to as the student's t distribution. So this t distribution, it has some properties, right? And this first one is, in a lot of ways, is the most important. The distribution is different for different sample sizes, right? This was the concession to making this work for small sample sizes, right? You had to tinker with the results based on the exact size of the sample that you're working with. It has the same general shape as a normal distribution. It has that same bell shape, although with some more variability. Standard deviation tends to be higher. It also has a mean of 0, just like our standard normal distribution did. And this last one, remember, they weren't really trying to replace the normal distribution. They were just trying to come up with something that kind of improved on it for small sample sizes. So as n gets larger, this t distribution gets closer and closer to actually matching up with a standard normal distribution. So I have here a t distribution table of values, and it is a little busier. There is a little more going on than there was in our standard normal distribution table. But this is doing something very similar. First, I want to be clear about what this table is giving us. It's a little bit backwards from what you're used to seeing with the normal distribution table. With a normal distribution table, the percentages, the probabilities, the areas are on the inside of the table, and the z-scores are kind of around the outside, right? They're in that top row and the left-hand column. With this t-distribution table, it's in the reverse, right? You see we have the percentages up here in the top row, and these numbers that you're seeing in the body of the table, they're not z-scores anymore. We just use z to talk about a normal distribution. So when we're talking about t-distribution, we're going to call them t-scores instead. So that's what you're seeing in the body of the table. All right, so to use this, the first thing you have to figure out is, do we want a one-tailed or a two-tailed test? All right, so in other words, are we looking for a situation where we want the percentage to be in here and I have two tails, or are we looking for a situation where I want the percentage to be in here and I have only one tail? Well, for what we're doing so far, this is an easy one. Confidence intervals are always two-tailed. And if you think back to the diagram we used, we're talking about proportions, right? It looked like this one, right? It had two tails. It's the same thing here. So when we're doing critical values for a confidence interval, we're always going to be looking at this two-sided row, right? And now the percentage, that is the confidence level, right? It's not alpha anymore. It is the actual confidence level. So you see up here on my question, I've asked to find the critical value corresponding to a 99% confidence interval. So I'm going to be looking in this column to get my answer, because this is the column that has 99% and is two-tailed. Okay, so now we've narrowed down the column. Which row are we going to use? Okay, well, this row over here is it's not always labeled. This row here is what we call the degrees of freedom. All right, the degrees of freedom, this is one of the easiest calculations you're ever going to do in statistics. The degrees of freedom is equal to the sample size minus 1. All right, that's it. That's all there is to it. So my sample size here is 13. So my degrees of freedom will be 13 minus 1. That's 12. So this is the row that I'm going to look in. All right, so looking in this column and this row, my critical value for this question would be 3.055. So if I were doing, if I were trying to do a confidence interval, right, this is the number that I would use as my critical value. In other words, as my t-score. Okay, so in the next lecture, we're going to use this new distribution to actually calculate confidence intervals, specifically confidence intervals for a population mean.